Hello everyone. I've been a little bit busy in my other work, so I couldn't record videos in between. So today I'm recording this video on on couple of very important topics, that those are quantum machine learning and quantum artificial intelligence. So let's talk about quantum machine learning and artificial intelligence little bit. So first I'll explain about these two fields little bit, and then I'll show some projects where we can implement rather these two techniques, quantum machine learning and quantum artificial intelligence. So let's begin with quantum machine learning technique. So quantum machine learning is basically the quantum computing analog of the classical machine learning algorithms or techniques. So it's basically an interdisciplinary field that combines quantum computing and classical machine learning techniques. It aims to leverage the principles of quantum mechanics to enhance and develop new machine learning algorithms, models, techniques and methodologies. So this is very important. In one of my research projects on cyber security, few months back, I was using this machine learning algorithm, this quantum machine learning algorithm rather, in my quantum computing cyber security project. So that was so in that case I was using the quantum computing analog of K-means algorithm. That was basically a clustering algorithm. Well, so I'll be explaining a little bit. I'll be explaining about that cybersecurity project using quantum machine learning algorithm that I've been using rather, and also I've written a paper on this cybersecurity project, and I have already submitted to IEEE journal. So that is in the process of peer reviewing. Well, so that's another part. So now today let's explain this quantum machine learning algorithm, rather technique or field more precisely, and some of the key concepts of this technique, of this field rather. So here are some key concepts and approaches in quantum machine learning, which are basically quantum computing, that is the inherent feature or kind of content of this technique, of this field rather. Apart from quantum computing, there are quantum algorithms also, quantum inspired classical algorithms, quantum data processing, quantum neural networks, quantum enhanced classical machine learning also. So let's little bit explain these fields, these topics rather. Well, so I hope you people know little bit about the quantum computing. That is basically, this is a resurgent field in this decade or the last decade as well. So this is the quantum computing. Basically it uses the quantum bits or qubits, that is the binary digits, quantum binary digits, that is called qubit. Qubit means Q for QU for quantum, and bit for B for binary, and IT for digits. So these are quantum binary digits, that is quantum analogues of the classical binary digit, that is 0 and 1, to perform computations. So unlike classical bits, that is 0 and 1, which can be either 0 or 1, qubits can represent both 0 and 1 simultaneously, and also not only 0 and 1. So the beauty of quantum computing is we can use both 0 and 1 simultaneously, and also infinite number of superposition states in between 0 and 1 by basically changing the arguments, the angles, basically the theta and phi, the two angles in between. Okay, so we can build up so many simultaneous states in between 0 and 1 as well simultaneously in quantum computing, but this is completely forbidden in case of classical computing or classical techniques. So this is the advantage of this quantum computing. Now this property enables quantum computers to perform certain computations much faster than classical computers. So I have used the quantum computers. I have used those kind of I've used quantum computers. I've run program. I've run codes. I've run projects on quantum computers. So that is much faster. So let's take an example. If suppose if a computation, if a calculation, a computation on classical computer takes maybe 7 days, that can be or 1 month rather, that can be done in basically few seconds on quantum computers. So we have done that. I'll show those things later on as well. Okay, so this is the basically the long short scenario of quantum computing. Now let's get into some quantum algorithms. So what basically what does quantum algorithms say? What do quantum algorithms say? Now quantum algorithms are algorithms specifically designed to run on quantum computers. These algorithms can potentially solve certain computational problems also more efficiently than classical algorithms. So as I have said, so in quantum computers it will take microsecond or femtoseconds or some seconds or some minutes. So to solve a very complicated year-long calculation on classical computer, so that can be done very easily on quantum computer. We have done that. Now some quantum algorithms like variational quantum eigensolver is one such algorithm, like you can call it QoA actually. So there are so many algorithms on one such variational quantum eigensolver. So we can solve the time independent or time dependent Schrödinger equation using that on the quantum argument on quantum using quantum computers very easily. So Google achieved this supremacy. They solved the 10,000 years problem in some femtoseconds back in 2019 on quantum computers. So that's a very beautiful project. You can read the paper. You can go through the paper that's published in Nature. Well, so now there are so many algorithms like variational quantum eigensolver, Grover's algorithm, Shor's algorithm, and these algorithms. I have one paper on Grover's algorithm. We basically use the optimal quantum search algorithms. That's basically we have expanded. We had expanded the algorithm that algorithm for more qubit systems and for using more number of gates, quantum logic gates. In my paper, you can go through my paper on Google. It's there on my Google Scholar also. So my group back then the director of Isaac Kolkata and two of my friends rather, one in the BSMS physics guy from IIT Kharagpur, who is in MIT now, and Kamal, and another one was from another one is now faculty of Kalinga Institute of Technology, KIT. So he has been in Isaac Kolkata. So anyway, our group, including the director of the my guide was director of the Isaac Kolkata. So we developed this. We expanded this Grover search algorithms. That is quantum algorithm. In case of more number of qubits and more number of logic gates as well, quantum logic gate rather. So Grover's algorithm basically uses 2 qubits and 2 qubit gate quantum logic gates, but we use multi-qubit quantum logic gates and multi-qubits also, multi-qubit line also. So we expanded this search algorithm and we were successful, and we basically named it optimal rather search algorithm, since it was giving us it was yielding optimal result. So well, anyway, let's get into the third feature, that's quantum inspired classical algorithm. You know, these are classical algorithms that are inspired by concepts from quantum computing but are implemented on classical computers. So for example, variational quantum algorithms such as variational quantum eigensolver, as I mentioned so many times in this video earlier on, that basically mimic the optimization processes that of the you know, the energy from the, or the solution of the both time independent and time dependent Schrödinger's wave equation, and that's basically they can be used easily in quantum computing but executed on classical hardware, right? We can use that. I mean, okay. So I will explain, and I will show basically hand on hand on my computer by accessing my quantum computing computer account, by accessing my account on quantum computers, several quantum computers. So I will show how to write codes or implement codes on Jupyter Notebook, and I will run those codes on quantum computer. I will show those things live hand on hand later on in other videos also. So now, quantum data processing. Now, quantum computers can potentially process and analyze quantum data more effectively than classical computers. Quantum data processing, you know, techniques could be beneficial for tasks such as quantum sensing, quantum cryptography, and quantum communication. Okay, so I'll explain these things later. I'll show all these things. Now, let's go to the fifth one, the quantum neural network. So neural network means is one subset of, you know, this artificial intelligence. This is basically the artificial, you know, build up of the human neurons. I mean the build up or artificial networks of human neurons, kind of, to mimic or to even work more efficiently than human brain. To solve more and more complicated problems. So that can be done in neural networks, and quantum neural networks are basically, you know, the quantum computing analogs of classical neural networks. Okay, so that's quite easy thing. I will explain all those things. There are so many neural networks, convolutional neural networks, other neural networks, also other neural networks. Okay, KNN, so many things, right? Yeah. Now, so these are neural networks. So what are quantum neural networks? Let's explain more precisely. Now, these are neural networks architectures, rather, you know, designed to run on quantum computers, right? So we can implement those things on quantum computer by using quantum computing techniques or quantum algorithms to solve more and more efficient, more and more rather complicated problems on quantum computer by using this, by basically building this artificial human brain networks, that's called neural networks. Well, so now, or utilize quantum inspired techniques also. Now, quantum neural networks can potentially provide advantages in processing certain types of data or solving specific problems, like such as optimization tasks or in maybe time dependent you know, wave equation or Schrödinger's wave equation and other things also. Okay, well, so also pattern recognition also. Yeah. Now let's go to another feature of this quantum machine learning, that is the quantum enhanced classical machine learning. Well, now in some cases quantum computing techniques can be used to enhance classical machine learning algorithms. For example, quantum computing can accelerate certain optimization algorithms used in machine learning, such as gradient descent or simulated annealing. So simulated annealing is basically is used in quantum annealing. That's one technique. Well, now quantum machine learning is still an emerging field, but very efficient field. I will show those things later on in my some projects. I will show one cyber security project where I will be using the quantum machine learning later on. Well, so this is still an emerging field with ongoing research and development. While there is a significant potential for quantum computing to revolutionize machine learning, you know, practical applications are still in their early stages, and many challenges remain, including qubit error rates. So what is qubit error rates? Let's define a little bit. So qubit error rates means whenever we are implementing some problems on some projects on quantum computers, so by using the quantum binary digits or qubits, that is 0, 1, and there will be infinite superposition states of 0 and 1 in between, having in between energy states, eigenstates, or maybe not even eigenstates also. So those things will lead to little bit of percentage of error error rather. So that can be calculated also by there will be error correction codes, other things. Okay, now the many challenges remain, like a qubit error gate rates, rather decoherence of the waves or qubits rather, and scalability. Nonetheless, QML or quantum machine learning holds promise for addressing complex computational problems that are beyond the capabilities of classical computers. As I've said, it can be done. I personally have done so many projects rather. So in one such project, I was running some, I had to get a very complicated time-dependent Schrodinger equations, solution, that is energy eigenstate. So I was a little bit stuck in that in between. So I then implemented the quantum computing. This is quantum machine learning technique, and basically I've been using the convolutional neural network later also, including also apart from along with other quantum machine learning QML in that. But I used efficiently the QML technique, and I got the results there. So that's the very juicy concept. This is quantum machine learning. I'll be implementing, and I'll be showing how to showing a project where we can see how we can implement the QML techniques or quantum machine learning techniques later on. So that's a very beautiful thing. Now, so to summarize, so in the quantum machine learning is basically the quantum computing analog of classical machine learning technique, and so many so many classical quantum version or quantum computing version more precisely rather. So it basically aims to leverage actually the principles of the basic quantum mechanics. That's very important. We have to learn that, and if someone is interested, you can go through the so many papers over there on QML. You can study all those. So this QML is very efficient. Also there is another thing, quantum artificial intelligence, that I will explain in another video. Okay, so that quantum artificial intelligence is basically very much efficient. QML and QAI are basically going parallelly in today's world, and we can solve very much complicated problems using very easily on quantum computers by using these techniques, these fields rather, quantum machine learning, quantum artificial intelligence, and all. So this is very important. We have to in our field of research, and in our daily life also, we can use these techniques to basically develop and solve very complicated physics problems, engineering physics and engineering problems, chemistry problems also, very easily within our time zone or time limit. Okay, so that's all about quantum machine learning today. I hope you have learned. I am able to make you understand, make you give an idea rather a little bit on quantum machine learning. Let's meet in we'll be meeting in another video later on, where I will be explaining. I'll be explaining rather the whatabouts of quantum artificial intelligence. Okay. Okay. Thank you. Okay. So thanks for watching. Bye.